Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problems 6 to 10 of the Algebra 2 New York Regents January 2015 released test questions. All right, so for problem number 6, we're going to be taking a look at the rule of the discriminant. We're going to be spending more than usual time on this problem just to make sure you thoroughly understand the role of the discriminant in describing the nature of the roots of a quadratic equation. So if you don't want a detailed consideration of this problem, you can always skip ahead to the concluding part where we will solve the problem. All right, so let's go ahead and talk about the role of the discriminant in the context of this problem. It says, which equation has real, rational, and unequal roots? Okay, so if you take a look at these equations right here, you notice that A, B, and C are rational numbers. Okay, so what we're going to do is create 4 cases um, where the discriminant can tell us detailed information about the nature of the roots. All right, so first of all, let's say we have a quadratic. Okay, let uh, ax square plus bx plus c equals 0 with um, a, b, and c um, as rationals. All right, so that's the standard form of a quadratic equation. Let's say a, b, and c are rationals. Then discriminant, let's call it the discriminant, let's call it d. And to find the discriminant, that's the radicand of the quadratic equation, right? The discriminant d, which is b squared minus 4ac, tells us the following about the nature about the nature of the roots nature of the roots of the quadratic. Okay, nature of the roots of the quadratic equation. Okay, so like I said earlier, there are 4 cases. Okay, let's look at case number 1. Let's title it cases. Case number 1, what if you have the discriminant with a negative sign? Let's say the discriminant is less than 0. If your discriminant b squared minus 4ac is less than 0, what does that tell you about the nature of the roots of this quadratic equation? Well, this implies that the roots are going to be, they're going to be imaginary, and unequal. Okay, imaginary and unequal. Case number 2, what if the discriminant is equal to 0? In this case right here. If the discriminant is equal to 0, then what you're going to have is you're going to have roots that are real, equal. This is known as the double root, okay? Real, equal, and guess what? And rational. Okay, rational numbers can be expressed as a quotient of 2 numbers, okay? So if the discriminant is equal to 0, you have 2 real roots that are identical and rational. All right? Case number 3, what if you have the discriminant having a positive sign? What if the discriminant is positive and it's also a perfect square? It's positive and a perfect square. If the discriminant is positive and it's a perfect square, then the roots are going to be real. If the discriminants is 0 or greater, it's always going to be real, okay? Because you're taking the square root of either 0 or a positive number, so it's always going to be real. The roots are going to be real. They're going to be unequal. And guess what? And rational, okay? One more case, case number 4. What if your discriminant is greater than 0, positive, and an imperfect square? Okay, imperfect square like 3 or 7. An imperfect square whose square root is not an integer. What is the nature of the roots in case 4? Your roots are going to be, you're going to be real, okay, because it's 0 and greater. They're going to be unequal. And guess what? They're going to be irrational because you're taking the square root of a number that's an imperfect square. So you're going to have that square root component in your roots. Okay, so these are the 4 cases using the signs and nature of the discriminant to determine what the nature of the roots of the quadratic will be. All right. Okay, now let's go back to the problem. So it says, which equation has real, rational, and unequal roots? So what we're going to do is we're going to take a look at these 4 options, find the discriminant value of all 4 of them, and then see which one is going to be which one will have real, rational, and unequal roots. Okay, so if you look at the 4 cases we have here, the discriminant that is greater than 0 and a perfect square is going to be real, unequal, and rational. That's what we're looking for here. Real, unequal, and rational. So we're looking for the options that match case 3. Okay, positive discriminant that is also a perfect square. So let's keep that in mind. Okay, so what we'll do now is just go through each option and calculate the value of the discriminant and use this solution to describe the nature of the roots. All right, let's take a look at option number 1. So for option 1, we have the quadratic equation, x squared plus 10x plus 25 equals 0. From this format, we can clearly see what a is. We can put a 1 here. So that's a, b, and c, okay? So we have, this is a, b, and c. So a is equal to 1, b is equal to 10, and c is equal to 25. What are we looking for? We're looking for the discriminant. The discriminant b is given by b squared minus 4ac from the quadratic formula, the radical component. All right, what's the value of this? Substitute these values into your radicand expression, and we'll have 10 squared minus 4 times 1 times 25. And then using your order of operations, we have 100 minus 4 times 25, 100, which is equal to 0. Okay, so this is case number 2, where we have a 0 discriminant. So since the discriminant is equal to 0, that tells us that the roots are going to be, they're going to be real, equal, that's a double root situation, and rational. Okay? Is that what we're looking for in the problem? We're looking for real, rational, and unequal, but we have equal, so this is not the answer we're looking for. Okay, so number 1 is not the answer. We'll advance to option 2. Option 2, we have x squared minus 5x plus 4 equals 0. And then this is, put the 1 here for a. So we have a, b, and c. Okay, so we're looking for the value of the discriminant. A is 1, b is negative 5, and c is equal to 4. Okay, so let's see. The discriminant d is equal to b squared minus 4ac. Okay, so if we plug in these values into this expression, we'll have negative 5 squared minus 4 times a, which is 1, times c, which is 4. Okay? I neglected to put a parenthesis here. That's a bad practice. Anytime you're evaluating an expression, substituting values into an expression, you always want to use parentheses, okay? There for your protection to prevent you from making um, errors associated with signs or powers. Okay, so always use parentheses when you're substituting, especially when you're working with the quadratic formula and the discriminant. Okay, so we have that expression there. Using the order of operations, negative 5 squared, this square impacts both the 5 and the negative, so we have 25 minus 4 times 4 is 16. 25 minus 16 is 9. So what does this tell us? It tells us that the discriminant is what? Positive. The discriminant is positive. Not only is it positive, it is a perfect square. Okay, so d is greater than 0 and a perfect square and a perfect square. So if it's greater than 0 and a perfect square, what case are we looking at here? Case number 3, greater than 0 and a perfect square. Okay, so let's go ahead and write down what this tells us about the roots. If it's greater than 0 and a perfect square, that implies that the roots are definitely real because you're rooting a positive number. They are unequal because it's not 0. And since this is a perfect square, they're going to be rational. Okay? And this is exactly what we want. If we go back to the options that we have, if we go back to the options that we have, we'll see that case number 3 corresponds with what we desire, real, rational, and unequal roots. Our answer for this problem is option number 2. Okay, so that's that. All right, let's take a look at problem number 7. So it says, which statement is true about the graphs of f and g shown below? So if you take a look at the graph, the function that looks like a staircase, the step function is g, and f is this rational function right here. Okay, so if you take a look at the options, we are classifying them as relations or functions. One of them is a relation, the other is a function. They're both functions, or neither of them are functions. Okay, so before we start to examine these options to see which is correct, let's talk about what relations and functions are real quick, okay? Let's start with relations. What is a relation? A relation is basically a set of ordered pairs, okay? If you see a set of ordered pairs, then you have a relation. Some examples of relations are collection of points, or you could have a line a segment, okay? Like you have here, you have a collection of segments. It could be a line or a curve. Um, these are relations because when you accumulate an infinite number of points, you get segments, lines, and curves, okay? How about a function? What is a function? A function is a set of ordered pairs, but there is also another condition that's connected to it. All right? A set of ordered pairs, graphically, the ordered pairs must create a situation that passes the vertical line test. Okay? So ordered pairs that pass the vertical line test. Okay? Vertical line test. This is just graphical interpretation of a function. Okay, so what are some examples of functions that pass the vertical line test? We have like rational functions, rational functions, like we have here. This is a rational function. Okay. Okay. Now let's take a look at the options we have. So let's start with G and F. Option 1 says F is a relation and G is a function. So Let's see. Is f a relation? The answer is yes. Why is that? Because any curve is a relation. Okay, we talked about that earlier. Relation is a curve, point, segment, or line. So f is a relation. True. G is a function. Is G a function? Does G pass the vertical line test? How do we do that? How do we carry out the vertical line test? All we simply do is we draw a vertical line, or you can use your pen or pencil, and then you sweep it across the entire domain of the graph, okay? And then you ask yourself, does the vertical line intersect more than one point in the entire domain of the graph? That's the question, okay? So let's see, right here, this vertical line I have, the question is, how many times does it intersect? We're looking at just the step function, okay, not the rational function. How many times does it intersect the step function here? Intersects only once, right? How about I move it over here? How many times does it intersect the step function? I'm sorry, the step relation. I don't know if it's a function yet. It intersects one here, once, there. So is this a function? The question is, can I find somewhere in the domain where this vertical line intersects more than once? How about I put it right here? What do you notice? There are 2 points of intersection. There's an intersection here and an intersection there. So what does that mean? It means G fails the vertical line test. G is not a function. Okay? So this part is false. Hence, option number 1 is incorrect. All right, let's move on to option 2. Let's put that vertical line to the side. F is a function. Is f a function? If we look at relation f, if we take this vertical line and sweep it across the entire domain of the rational function, does it cross more than once? Okay, let me highlight the rational function. I'm talking about this one right here. This one and that one. Oh, that's not good. Anyway, the rational function is this piece. All right, so does it cut more than once at any point in the domain? Let's go ahead and sweep it. So you see once, 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 once. Here you have an infinite discontinuity, once, 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 once. So for the entire domain, the vertical line intersects the graph at exactly one point. So what does that mean? It means that f is in fact a function. Okay, so f is a function. Is G a relation? Absolutely. Remember we talked about ordered pairs or collection of points. So we have segments here. Segments are a collection of infinite number of points. So f is a function and G is a relation. So that's correct, and the second option is correct. So we're confident that our answer is option number 2. Okay, so that's that. All right, let's take a look at problem number 8. Problem 8 asks the common ratio of the sequence -1/2, 3/4, and -9/8 is. So common ratio is what you keep multiplying over and over again to generate the terms of a geometric sequence. Okay, the formula for common ratio is a 2 over a1, or let's put equal to a2 over a1, which is equal to a3 over a2, which is equal to a4 over a3, or generally speaking, an over an plus 1, an minus 1. What does this mean? It means that if you divide a term by the term before it, you generate the common ratio. Okay, so in this case, the first term is a1, this is a1, this is a2, this is a3. We can divide a2 by a1 or a3 by a2 to generate the common ratio. It doesn't matter which one we pick, okay? Just make sure that they're consecutive terms. So I'm going to use the formula a2 over a1. Okay, you can use a3 over a2, you get the same answer. So a2 is 3 over 4 divided by a1, which is -1/2. All right, so I'm going to keep change flip or drop change flip. I'll drop the numerator 3 over 4 and multiply it by the reciprocal of the denominator negative 2 over 1. Okay? So dividing is the same thing as multiplying by the reciprocal. So what we'll do next is let's reduce. 2 goes here once and 2 goes here twice. If you multiply uh, horizontally, 3 times negative 1 is negative 3. 2 times 1 is 2. Your common ratio is negative 3 over 2. Our answer is option number 1. All right, let's take a look at problem 9. Problem 9 says, how many different ways can teams of 4 members be formed from a class of 20 students? So one question most students will have is this a permutation problem? Or is it a combination problem? Okay, so don't forget, whenever you see permutation, to think about placement. Okay, permutation is all about placement, or you're arranging placement or ordering. If there's a particular order or pattern that you're arranging the elements that you're choosing from, then you think about permutation. Placement, ordering, position. Okay, positioning of elements of a set. And combination basically has no placement, no order, nothing like that, okay? So the two possible choices you might think of is, if it's permutation, is going to be out of 20, you are placing 4. You're arranging 4 elements out of 20. If it's combination, this is no order. You're free to choose, okay? You're going to be choosing, out of 20, you're going to be choosing 4. So which is the correct one here? All you have to do is read the problem carefully and closely. You're selecting 4 members. Are they being arranged in any particular format? The answer is no. There is no order in which these 4 members are being arranged upon selection. Let's say that there were spots like first position, second position, third position, fourth position. That's placement. Or let's say there were titles that these 4 members were being assigned, like the president, vice president, secretary, and something else. Then that will indicate permutation. Since you're just selecting 4 members, you're choosing any 4, and order is not important here. So is this permutation or combination? It's permutation, not, I'm sorry, it's combination, not permutation. Okay, there's no order involved here. So this is not the right one. We're going to be using 20, choose 4. Okay, so let's go ahead and do this with our calculators. All right, I'm going to be using the TI-83 calculator to compute the value of this combination. So we will enter the number 20, and then we're going to be choosing 4. So you can go to catalog, see second function 0, catalog, and you scroll down to N for combination. So let me just press the N button. Okay, so NCR, this is for combination, okay? And then NPR is for permutation. So this is what we want. N, so 20 is N, R is 4. So choose 4, enter. 4,845 different groups of 4, okay? So that's our answer. 20 choose 4 is 4,845. Our answer is option number 3. All right, let's take a look at number 10. It says, if sine A is 3 over 8, what is the value of cosine 2A? Okay, so this is assessing your ability to apply the double angle identity for cosine, okay? So we have cosine 2A here. So I grabbed the double angle identities from the reference sheet and I placed it here. One interesting thing about the double angle identity for cosine is that you have 3 choices to select from. Okay, so in this problem, you're provided with sine and you're looking for cosine 2a. Out of these 3 options, which is the best one to use? we want to pick the one that's only dependent on what we have, which is sine A. So that means that the third option will be optimal right here, okay? So that's what we're going to use. We're going to use the identity cosine 2A is equal to 1 minus 2 sine square A. Okay, so 1 minus 2, we're going to substitute the value of sine A into this formula right here. So we have 3 over 8 square. Now we will just carefully apply the order of operations in simplifying this expression. So we have 1 minus 2. Now when you're squaring this fraction, don't forget to square both the numerator and the denominator. Okay, so that yields 9 over 64 times 2 over 1. You can reduce this by dividing by 2. 2 goes here 1, 2 goes here 32 times. Multiply across, you have 1 minus 9, 9 times 1 over 1 times 32, 32. Now to combine these two, we have to express this as a fraction. The LCD of 32 and 1 is 32, so we times it by 32 up top and bottom. So we have 32 over 32 minus 9 over 32. 32 minus 9 is 23 over 32. And that's the value of cosine 2a, option number 3. Thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to the remainder of this review series. We'd like to know what you think. If we get at least maybe 20 thumbs up, then we'll know that this presentation is pretty cool, and we'll do the next ones from here on out, okay? More clips can be found on math.serve.com. Go ahead and check that out. Thanks again for watching, and have a wonderful day.